So welcome everyone again. My name is Jorge Quilcate. I'm a software engineer at Aiven. I work as part of the Kafka team for more than a year now. And Kafka Tier Storage has been kind of the main project that I have been focusing on. And it's been a kind of an interesting ride for all this time. And it's a project that it's open source, first of all, so we are adopting the open source implementation of tier storage. And we also kind of need to do all the preparations within our data platform to onboard it properly. So we will see kind of what that means later. And basically tier storage and there's been sort of an increase on improvements and sort of a re-architecture of Kafka as a project, as a software platform. So Kafka has been open source for more than 13 years, and it starts to show its age. It was developed kind of for a certain age when, the cloud wasn't ready yet. It was mostly on-prem, and there has been a tremendous change on how do we deploy things, how much load do we put in this type of data systems, and so on. So there has been two major changes in Kafka happening over the last 3 years. One of them is probably you might heard of that Kafka is removing Zookeeper at some point. So if you are not aware, we are at version 3.7 now. 3.8 is supposed to be the last version with Zookeeper. And 4.0 will be only KRaft, or the kind of query metadata management, all within Kafka itself. So Kafka is kind of sort of evolving how it manages metadata. But in this talk, we will talk about this sort of second evolution or great change happening in Kafka, and it's about how data is stored. And currently, it's a share nothing type of architecture. You have a broker has disks, it doesn't share with anyone, right? So we are kind of hitting some limitations on that architecture, and we need to rethink how it's kind of going to move forward. And that's kind of what tier storage is about. So this tier storage initiative has also been running for a few years, and finally has kind of become available since 3.6. Now we are sort of discussing with the community, are we ready to call a GA? So maybe next releases are going to we are going to take that step, and sort of it will become a standard way of how to store data in separate layers. But so this presentation is about sort of an infrastructure feature, so it's not that exciting. You cannot do kind of code stuff or anything. So this will be more about sharing our experiences, looking into the data flows where tier storage impacts your workloads, and showing some numbers, some benchmarks, and hopefully that can give you a feel of how it works, what is the impact that I should expect as an adopter of this feature. And we can discuss further. So let's take a quick recap on how storage works in Kafka. So Kafka, when it was designed like 13 or more years ago, it's a system that has been designed about around the file system. And don't fear the file system. It was that was kind of all the design of Kafka has been around how to efficiently manage memory within the JVM, the memory that you have available in your brokers and disks, and how the kernel does all this heavy lifting of unified cache or called page cache and move the content from the files directly from memory into disk, how to do that efficiently, how to do read ahead type of operation. So all the design of Kafka tries to leverage this ability already available in kind of Linux kernels. But this, as I mentioned, this is a share nothing architecture, and it has hit some challenges. One of those challenges comes from the requirements on using Kafka. So Kafka has grown, like the growing adoption of Kafka is difficult to compare with any other data system. It has become like the de facto on how to stream data, how to connect systems, and so on. So the amount of data that you have to deal with Kafka just keeps growing. It doesn't mean like it's not just for keeping data longer, but just kind of the use cases that you need to onboard force you to keep larger amounts of data within your brokers. And that starts to become a problem. And if we don't deal with that properly, we basically block the adoption of Kafka further. So we want to remove these blockers. One of these blockers is the operational complexity that we have to deal with when we operate a cluster that has a ton of data, like terabytes. And that operational complexity comes when you have to actually move that data. Rebalancing, replacing brokers, replacing disks becomes a very expensive operation. You have to usually move all of that across the network. And the other blocker is the costs. So keep extending local disks becomes really expensive. Usually this needs to take into account replication, so you have to actually extend it 3 times. And usually you want to keep a bit more capacity, so you usually have to double that again. So it can become quite expensive to keep data in local disks. If you compare it now with the current state of object storage, is like S3, you can get like 20 times cheaper storage of a gigabyte compared to keeping it locally. So that's the other 4. So on one side, we have this complexity on how to operate Kafka. On the other side, we have the reality that object storages have just become so largely adopted. So people trust them, and they have a kind of a scale that you cannot compare with, gives you this ability to have sort of an infinite retention. There's nothing like really you need to think about capacity anymore if you have integrations with this type of systems. So those are the 2 drivers, I would say, that kind of force us into redesigning Kafka. So there is actually, it's a very hot topic at the moment. If you have followed sort of the new projects that are starting to be released around this topic, there is new initiatives, new companies being built around, and trying to go all the way into S3, actually, kind of just forget about disks. Let's go all the way into S3. And they have some actually thought-provoking ideas that you may be interested about reading. But let's look into kind of how Kafka has evolved in this way. So basically, Kafka has this concept of retention. So you store data in Kafka. The data is stored in files. These files are sort of ordered by time and by offsets and positions. And you basically decide how long do you want to keep this data. It's very we are just piggybacking into this idea of retention to enable us as users to define how much data do you want to actually keep locally. And so now you will be able to say, okay, I want to, from my retention that could be a week or 2 or a month, I want to keep this few hours of data locally or these few gigabytes of data locally, and everything else should be kind of delivered to my remote layer, and it should be transparent for my users, so customers shouldn't care about. So that's pretty much the idea of tier storage. That's why it has been implemented, at what challenges it tries to cover. But let's take a deeper look into kind of how the internals work a bit, and how the data flows around tier storage. Actually, the data flows that care kind of for you as a user or as an operator or as a developer. And let's see how it goes and show some numbers. Like I tried to run some benchmarks this week, so let's see if those are of interest. So internally, Kafka was designed, as I mentioned, to keep every broker has a complete view of the topic. Right? Everything is within the broker. So usually this was the only abstractions that you have in Kafka: a replica manager, a log manager, and the log, the abstraction of the log. And everything was there. Now, if we actually want to onboard this new layer of data, we actually need to know much more about it. So the broker is not enough. And so the architecture of Kafka is basically a hierarchy of managers. Now there is something called remote log manager that will take care of giving us the view of how the remote layer looks like. And basically the abstraction of a log has been extended. So now there is something called unified log that has the local log and has the reference to a remote log storage to complete the view of the topic. So this doesn't, how this has been designed is to have a pluggable architecture. So we have on one side how to deal with the actual storage, so uploading, reading, deleting data from the remote layer, from the remote storage. This is called Storage Manager, Remote Storage Manager, or RSM. And then we have to actually give metadata about these remote logs. So we need to know if they had been uploaded, if they had finished the upload, if they have been deleted, and so on. So we have a local view of what the data remotely looks like. We as Aiven, so Kafka comes with a default implementation of the metadata manager. So we keep everything in a topic. But the actual integration with the remote storage is not included as part of the Kafka project. So you actually have to kind of add your implementation into the configuration. So what we have done is implement this interface with a plugin that is actually like you can use it with multiple, basically with the vendors that we are more focused at the moment with S3, with Azure Blob Storage and Google Cloud Storage. So you basically have the same plugin. You can configure it for your object storage. And that's what we will look at the moment. But now something to be aware of is that your data is not fully interbroker anymore. So you will have some logs that are the local ones. You will have the metadata in a topic, and you will have the remote logs through that will be managed through the plugin. So that increases a bit the complexity. Like you have to kind of just be aware that data will be, if you want to run this yourself, you have to be aware of all these different parts and take care of them and monitor them and so on. So in Kafka, what data is available locally? So locally, we have usually the segment that keeps the data. So we have records. Records are usually batched, and these files keeps all the batches in orderly manner. So to access those log segments, we have a couple of indexes, one for offsets that are the positions of your records. So it's basically a binary search that tells you where, for this offset, where is the position of the file that I should start reading from. And then we have a time index for, basically doing the same, but for time. Then we have some additional indexes that are important to be aware of. The leader epoch that tells you who is the leader that actually wrote this file, because the leaders basically rotate or change over time. And the producer snapshots and transaction indexes that helps you to, so those are important bits when you work with transactions. So basically keeping track of the producer IDs, keeping track of your transaction, the aborted transactions. So you can give them back to the consumers and they can, ignore some messages and so on. So all these sort of files are kept locally at the moment, but we actually have to ship them into a remote storage. So what we have at the moment, as I said, we have the remote files. So first we actually have to take this log segment file that usually is a gigabyte or hundreds of megabytes of size. And of course, we don't have to ship, we don't ship it directly. We add some features to compress them, to encrypt them, and actually we have to chunk them to get an idea of how to read data efficiently in the cloud. So the file at the end may look a bit different than how it looks locally. Then we have a concatenation basically of all the indexes into the same object, and we ship them. And then we have a manifest that basically is the index for the remote log segment. So we have an additional index to efficient reading. Apart from that, there is all these sort of events that will be stored about your data that is shipped remotely. So you will have events telling you when this copy started, when it finished, if it was deleted, and if that deletion has completed. And that sort of tells you the life cycle of the remote segment. So let's look into, so now that we have a clear, an initial idea of how the architecture of Kafka has evolved to support your storage, and kind of how the local data and remote data and metadata look like, we can share a bit kind of what are the patterns that we have found so far. So we have been running a few months tier storage in Aiven as an early and a beta future. And we basically, if I can categorize it, I will say there's these two type of scenarios. And let's see kind of how much impact do they cause. So the first one is if the producers and consumers are mostly on hot data. So if you have workloads where your producers and the consumer lag that you have are usually small. So let's say you actually monitor and have SLAs on how far behind the producer you could be, and if not, then you have alarms and basically a way to that's an incident if you kind of fall out of your consumer lag. Then you usually kind of keep those two quite close together, and if they are quite close together, or at least within few minutes or even within few days, data will most probably in most common configurations be available locally. So for producers and consumers, there is actually the expected results is that producers and consumers get no performance impact. So they are, as usual, reading data and writing data locally. And the brokers will just get the additional work of actually shipping this data into object storage. So I would say this is, in my sort of expectations, this will be kind of the 90% of use cases, maybe 80. And on the other hand, I've seen other patterns where there is actually workloads that need to reprocess data. And maybe this pattern will start to grow more and more because now everyone wants to build models and rebuild models and reread data from the beginning and maybe create something different. So this actually will put your consumers in a position where they will most probably read data from a remote storage, and you actually and the amount of data that they will read is quite considerable. So in this case, when they hit remote, they will definitely get kind of, obviously data is remote, it will go through the brokers, there will be a performance penalty. But what we are thriving to is to actually make that performance good enough so you can still onboard your use cases. And it's a bit of what I will try to show you in a bit with the performance impact benchmarks. So if you are going to adopt Kafka to your storage and you are a developer, you actually, as a producer, you don't have to do anything. All the uploading happens asynchronously and is managed as a separate thread in the broker, so there is no impact on producers. Consumers do not have an impact neither, but we have hit this sort of back in 3.6, so if you're and 3.7, but we have a patch in our version, so I don't worry too much about it. But there is a keep. So the keeps are basically the improvements in Kafka, and there's a bunch of keeps now related to tier storage. So basically, you have, as a consumer, you have a timeout, how long to wait for data. And usually that timeout is thought or is set thinking in local data, but now data is available remotely, so the timeout is usually too short. So we are removing that approach and we are defining a broker configuration that will define the timeout. So consumers will not have any change. And yeah, we will fix this. Or we have already fixed it in our fork, but it will be fixed upstream as well. On the operator side, so if you're operating Kafka and you have Kafka kind of on-prem or you manage it yourself, you will have to enable remote storage, so basically the flag to use your storage. You will have to set up your storage manager and your metadata manager, set up your implementations and configurations. And on the topic level, so on each topic, you will have to say this topic has remote storage available, and how the retention will work for that topic, right? So you can say like local retention. You can start like the default configuration is basically you enable tier storage and you keep everything local and remote. So that's as safe as you can go. Like you are not actually removing data locally. You can just enable it and see how the upload actually impacts your workload. It should be very low, but you can test it on your environments. And then start like tuning the local retention, so you start to get the benefits out of having the data remotely and don't having to like read everything or keep everything locally. So now I would talk about I will show some metrics, and so the setup for the benchmark basically is using Aiven for Kafka. I use a plan that gives us like this amount of infrastructure, 4 CPUs, 16 gigabytes of RAM, And for clients, I spin up like 6 clients, and there is this very interesting tool called Open Messaging Benchmark that actually has a lot of options, and one of them actually really help us to test tier storage in an interesting way. So I will show you a bit of that. So I basically create a topic, 12 partitions, put some load, like 64 megabytes per second, and segment size is 200 megabytes. And I try to keep as less data locally as possible, so I can try out the deletion and so on. And basically the backlog is the interesting part. So let me show you how this looks. So this is, so we have producer workload on the top, so it's around 64 megabytes, and we have the bytes out on yellow. So what you see here is at the beginning there is a warm up, so the workload starts and it tries to push the kind of 64 megabytes per second and read them just to warm up your cluster. Then you have at the end the same workload that you define for an amount of time. So I put like 5 minutes here, so there is not much there. But I really care about the in-between here. So this benchmark, for instance, can help you to build a backlog. So you just write for amount of time, or you want to, in this case, I want to kind of write for this 120 gigabytes. And then I want to write long enough. So I have some data remotely, and I can sort of benchmark, show you kind of what's the impact reading data from remote. So it starts the consumer at some point. There is a large consumption, and then it goes down to the kind of expected real-time read. So that's the benchmark. I will show you kind of how it affects the data flows. So the uploading data remote logs. So as a producer, and you have no tier storage, this is how it looks. You just write, segments are rotated, you keep some retention and so on. If you enable tier storage, now you have to define a local retention. So you will keep some data locally, and some data will need or will become candidate to be uploaded. As this is happening, the candidate segments are passed to the plugin. So the plugin, as I mentioned, has this ability to chunk the data, to encrypt these chunks, add compression. And the last feature that we just added this week was rate limiting. And rate limiting is kind of very important because we really want this to be as predictable and low impact to your broker as possible. So you can define like a fairly low, like with I try with 5 and 10 megabytes per second. So that's the maximum throughput that this background job will use for uploading data. So it doesn't bother with your workloads, and you can be kind of safe to start using it. Then we have all these storage backend specifics, and hopefully at the end we have remote objects for this input data. You already mentioned kind of this is the data you will get on your S3, for instance, and the events that will get created. So this is the baseline for kind of how the cluster looks when I just writing. So the first part, building the backlog, right? So I just have a producers writing into the Kafka broker. It has 12 partitions. All the brokers sort of get the same CPU utilization. And network-wise, this is how it looks like. So on the top part, we have the input that is around 200 megabytes. So it's the producer rate plus 2 times the replication. So how the brokers get data in, and on the part on the bottom is how much data is out. So around 140, that is the replication basically. So with your storage and a rate limit of 5 megabytes, you can see that it's just got sort of a bit higher. Like it was, I think, 34. Here we are talking about 38. Impact on kind of CPU consumption. And now how it looks like in the throughput. So we expect to get this 3 times the actual upload rate on top of my replication. So you will get this sort of 15 additional bytes that you have to deal with. But that will be it. That's the upper bound. The idea is to just make it predictable, make it safe and boring. And that's it from the uploading. The uploading is successful. We get the data on the S3. Now the broker can start to remove the all data from the local, that is outside of the local retention. So if you kind of do not have tier storage, then the data stays there, right? So we have around like 160 gigabytes here. So if you enable tier storage, you will get this gradual removal of segments. And yeah, depending on the uploading rate, depending how aggressive you need to be actually. So we are between 5 and 10, I feel that is a good initial setup. So you can see data is being deleted and uploaded. And this upload rate limit will tell you how long the uploads will take. So here's between 2 and 3 minutes for each segment. If you increase the rate limit, of course, you will get kind of faster deletion and faster availability of the local data. So it's something to kind of a trade-off, right? You can see below 2 minutes to upload data. And yeah, deletion is boring. So once the data remotely is outside of the retention window, it gets deleted. So, but there is nothing to. You will just get data deleted from the remote and the events confirming that it has finished. So that's, let's say, the archival part, like uploading and removing data out of the S3. On the other hand, we actually have the fetching of this data, and this could be more interesting depending on your workloads. So we have, when there is no tier storage, everything is local. You can just read or reprocess as you want. If you enable tier storage, as I mentioned, the data start to be shipped remotely, but they will stay locally until kind of the recurrent work thread for removal is actually scheduled. So you might still hit data that is outside locally if there is available. But at some point, data will be removed from, and you will get some requests to actually read data that is only available remotely. And that's when actually our plugin starts to work on that side. So here we get, we usually use a range fetches from object storage providers. So we just kind of gradually start reading data. We have some decompression, decryption, and that is optional. But we also have some chunk caching and prefetching. So we can actually start, if we get a request for a certain range, we can start like getting that data cached locally. So the next request to consume the data is actually going to get it from local. Doesn't need to go all the way up. And finally, you should get your record batches as you used to. So let's look at the benchmark. So in this case, this one is without tier storage. So you can see, gets quite performance. At the beginning, there is the warming up time once the consumer is started. So it starts to read slowly until it warms up and gets up to 500 megabytes per second. And this is for the cluster, so all the 3 brokers. So no tier storage. At the end, it catches up, and the same input and output work throughput for that. So how it looks like with tier storage. So in our case, like because we have a very low rate limit, it means that removal of local data takes longer. That means I have few data that is only available remotely. So in this case, you can see we are getting at the beginning of the consumer of the consumption of the backlog, we are getting just the kind of fetches from remote. So remote is kind of sourcing all of our requests at the beginning. So I think it's around here that it consumes all the remote data until it hits data locally, and then it picks up and reads as local. So you get some increment on the latency, but the throughput, you can see that is still large enough. So 64 megabytes for 2 or 3 partitions available in each broker, or 3 or 4. I would say 4 partitions per broker. So that sort of gives you an idea of the throughput that you can get, and is that enough for your use case is something we can discuss for sure. And in this case, with having an upload rate limit higher means I can remove data faster, so the actual reading from remote is longer, and you can see that clearly here. So I'm reading from remote at here, then I'm picking up with local data. I'm picking up with remote data, and then go back down again. And again, around it was 6 minutes without tier storage. It's around 11 or 12 with tier storage. So that gives you an idea, okay, how much longer I would take to process this data, but then kind of it's a trade-off, and you get some of the benefits. So CPU-wise, the consumption, you can see here the idle CPU. So it's around 45 without tier storage. It's 39 with tier storage, so like around 5 to 6 more CPU consumption, I would say. So it's kind of at a state that we say it's okay. Like we don't get like double CPU consumption or something that really worries us. So in that case, also reading data and fetching. And when the fetching happens, it's also uploading on the background. So I would say the impact is manageable. So just to show kind of for a single partition, so you can see, okay, for a single partition, how much can I get? So for this plan, the business 16, we kind of get up to 40 megabytes per second from a single partition. So that can give you an idea, okay, my use case requires more than this or less than this, and evaluate whether to start reading from remote. How many good time? 3 minutes. Okay, cool. Let's go. So that's pretty much everything about the data flows that you will get as an operator, and shipping data and reading data from tier storage. But there is some additional work that we, as someone who is going to operate Kafka cluster, have to do. So you have this metadata in a topic that tells you the source of truth for the tier storage data, but you have the objects in a separate storage. So you actually have to keep consistency between these two. And if there is any divergence here, so it might be like orphan files, or it might be like files that has been removed but should be there, that should trigger alarms. And that's something that we have built already, an internal sort of consistency model that help us having a clear view of the metadata. So we build sort of a local image on every broker of how the metadata looks, so we can query and kind of do some operations there. And also it kind of checks with object storage, is this data there? It has been removed, it's available or not? And that should give us kind of enough. So far, it hasn't ring the alarm yet. So that gives us confidence on kind of moving forward. So it's important to kind of keep in mind that apart from the setup, there is additional monitoring that you have to keep in mind if you are onboarding to storage. But it's nothing crazy. And this one is just an additional, like a simple metrics on how the rebalance works. So I'm replacing all the brokers. I'm bringing new brokers. If I'm without your storage, it takes, I haven't put the time here, but it takes around, I think, like 30 minutes. When we enable tier storage, it takes about 12 minutes. Well, it really depends on how much data you have locally. There is no science here. It's just kind of moving the data that is available locally. So you get that. This is probably for us as Kafka operators, this is the most important benefits. We can have faster rebalance that give us better user experience. I have probably 2 minutes. So let's look quickly into what's coming upstream. So upstream, we were basically discussing today with some of the committers what is missing to actually call this generally available or production ready. And there's a few keeps that are important, but I think the first one is probably the one that we really want to have before we make this call. That is the tier storage disablement. So you are able to go to a topic and say, I want to disable tier storage. So it will do the arrangements, and you are safely going to take our a topic out of your tiering. So that should give enough confidence to actually make a production ready call. The other ones are also improvements like quotas for tier storage. The followers will start to get much more speedy on recovery because they will know which state is remote. So that's coming up upstream. On the plugin side, we also have some ideas. We are really happy with kind of the upload rate. So from here, I think it will be more like bug fixing and maintenance, but we have some ideas on how to improve further the performance, mostly on reading. I think reading is the part that probably we will get more requests from. So we have some ideas on, for instance, how to do, we can do prefetching on a single segment, but if we actually want to go do it across segments, it's not possible at the moment. So we really need some signals, additional signals from the API to actually make this possible. And it's been proposed, but probably it's not priority at the moment. Hopefully it will be. Yeah, some improvement on caching. So wrapping up, we try to recap a bit of how the storage layer works in Kafka and how it's evolving. What challenges your storage is trying to target and solve, and sort of what are the motivations behind it. Hopefully the internals give you a guidance on kind of how much has changed internally in Kafka, and what are the usage patterns that we have seen and the performance impact. And yeah, knowing what's coming and how close we are to generally available, I think hopefully it's also useful for you to start trying. Yeah, you can try yourself in Aiven. We have it available. And thank you. I think that's all I have.